Welcome back. In the last session, we have completed the general and physical properties of alkali metals, except one property, that is flame colorization. What is flame colorization means? Alkali metals produces characteristic flames when they heated under Bunsen burner. When the alkali metals heated to Bunsen flame, they gives characteristic color property. Due to that characteristic colors, we can identify the given respective alkali metal. Lithium gives crimson red color, sodium gives yellow color, potassium gives violet red, rubidium gives violet, cesium gives blue. What is the phenomena involved in the giving this characteristic color when they heated to Bunsen burner? Means, see, we have one outermost electron in the last shell of this alkali metals. When we provide some heat in the form of energy, when we provide some energy in the form of heat, the electron present in the ground levels undergoes excited state. While the excited electron coming down, they emit some energy in the form of radiation, in the form of photon in the visible region. While the energy is releasing in the visible region, these characteristic colors can be shown by these alkali metals. This color property is very important, and we can use this color property to identify this respective unknown alkali metal. This is about the flame coloration. And next, after general and physical properties of alkali metals, we will discuss about the chemical properties of alkali metals. Chemical properties of alkali metals. In our last session, we have discussed about the reactivity of alkali metals. Alkali metals are highly reactive in nature. These are highly reactive in nature. The reactivity of alkali metals due to one is large atomic size, low ionization potential, low heat of atomization, and high electropositivity. Due to these reasons, the alkali metals are highly reactive in nature. So, the occurrence of this group elements, this first year group elements, will be in their compound form but not in free state. When they do not have any reactivity, then those elements will be exist in their free state, but these elements can exist in their compound form as they have reactivity high. The high reactive nature of alkali metals due to these following reasons. One is large atomic size. If atomic size is more, its ionization potential is less, and next low heat of atomization and high electropositivity. These are the reasons to show highly reactive in nature. The chemical properties towards some respective reactants we have to discuss now. One is reactivity towards oxygen, reactivity towards water, reactivity towards hydrogen, reactivity towards halogens. In this first one, we will see reactivity towards oxygen. When they react with oxygen, the compounds formed are called oxides. So when alkali metal react with oxygen, the products are called oxides, and when alkali metals reacts with water vigorously, they forms MOH type of hydroxides. When alkali metals react with hydrogen, they forms MH type of hydrides. When they react with halogens, they form MX type of halides. We will see individually about the chemical properties of alkali metals with these following reactants like oxygen, water, hydrogen and halogen. So the first reactivity or the first chemical property of alkali metals is reactivity towards oxygen. When alkali metals heated, alkali metals are heated in presence of excess of air or excess of oxygen, they form mainly three types of oxides. So those are M2O type of monoxides, M2O2 type of peroxides, MO2 type of superoxides. After the formation of these type of oxides, immediately they contact with moisture present in the atmosphere and forms hydroxides. Further, that hydroxides contact with carbon dioxide also present in the atmosphere and forms carbonates of these alkali metals. Let me take the oxide of alkali metals like M2O. When M2O contact with moisture present in the atmosphere, they form MOH type of hydroxides. Further, these hydroxides react with carbon dioxide, they can form M2CO3 type of carbonates with the formation of water. Means we required here 2 moles of MOH, M2CO3 plus H2O, that is the balanced equation. So to avoid these continuous reactions, we will store these alkali metals in one organic solvent or one hydrocarbon solvent like kerosene oil. When we store these alkali metals under kerosene oil, we will prevent the contact of alkali metals with the atmosphere. Therefore, we will prevent these chemical activities so that we have a chance to get these alkali metals in their native state or in free state. As the density of these alkali metals is very less, we can store those alkali metals in the hydrocarbon solvents. So when these alkali metals react with oxygen, they form these three types of oxides. Especially these monoxides are formed by only lithium, these peroxides are formed by sodium. The remaining oxides means the remaining elements can form this type of superoxides, nothing but potassium, rubidium and cesium. So what is the reason behind the formation of only monoxides by the lithium is the question. See, this lithium plus, due to its very small size, this lithium has a chance to prevent the bond formation or the bond between oxygen and oxygen in O2. So due to very small size of lithium plus, it prevents the bond formation between oxygen and oxygen like in peroxides and superoxides. So this lithium plus only can contact with oxide ion and forms this type of oxide which is called lithium monoxide. From lithium plus to sodium plus, size increases. Larger the size of sodium plus, the sodium, especially the sodium, can form two types of oxides. One is Na2O type of monoxide, Na2O2 type of peroxide. When limited amount of air or when limited amount of oxygen, when we pass towards the sodium, it forms Na2O type of monoxide. When excess of air, means in presence of excess of air, sodium forms sodium peroxide. As it is making this peroxide, the sodium plus ion is able to prevent the O bond O in superoxides, but not able to prevent the bond formation between oxygen and oxygen in peroxides. That's why this oxygen directly contact with peroxide ion, which is nothing but O2 minus 2. And from sodium plus 2, that other univalent positive ions like K plus, Rb plus and Cs plus, due to very large size of these ions, very low positive field is there around these large sized ions. Due to this reason, the large sized ions cannot prevent the bond formation in superoxides between oxygen and oxygen. That's why they can give their outermost electron to oxygen molecule. Therefore, oxygen molecule can form superoxide ion called O2 minus 1. However, we are getting these three types of oxides. The oxidation state of alkali metal follows only one type of oxidation state, that is M plus 1. Whether in M2O type of monoxides or in M2O2 type of peroxides or in MO2 type of superoxides, the oxidation state of M is always same, that will be plus 1, because we know the reason. They have only one electron in the outermost shell. That's why they need to lose that one outermost electron and forms unipositive ion. That's about reactivity towards oxygen. When they react with oxygen, they are making three types of oxides. In all those oxides, the oxidation state of alkali metal will be same, that is plus 1 state. That's about reactivity towards oxygen, and the products are called oxides. The properties of oxides we will discuss individually after the reactivity properties of these alkali metals. Next, reactivity of alkali metals towards water. Alkali metals react with water vigorously and forms respective MOH type of hydroxides. M, when react with water, they form MOH type of hydroxides with liberating hydrogen gas. So 2H2O we require, 2MOH and 2M is the, so that is the coefficients required while we are balancing the equation. So they are making MOH type of hydroxides which are bases. The properties of these hydroxides we will discuss later. The reactivity towards water increases down the group. Due to this reaction, we can confirm that these alkali metals are strong reducing agents. The reducing nature of alkali metals will be depends on capacity of alkali metals to take part in oxidation. Oxidation can be takes place for alkali metals in two ways. One is M changed to M plus 1 electron. Loss of electrons or increase in oxidation state is called oxidation, or this reducing nature also decided by releasing capacity of hydrogen from the water. Reducing nature decided by releasing capacity of hydrogen from water. Not only from water, from the compounds containing acidic hydrogens. For example, like alcohol or mineral acids we take. Whenever we take the alcohol, the alkali metal, the common formula of alcohols is R bond OH. When they react with these alcohols, they form R bond OM with liberation of H2. Means we require 2 ROH, 2 ROM, 2M, and hydrogen gas will be released. Or you take mineral acids, the general formula for mineral acids like HCl, here I am taking HX. When they react with the HX, the hydrogen will be displaced from acids. Being these are metals, one of the important property of metals is displacing hydrogen from the acids. So these alkali metals also displaces the hydrogen from the acids and produces hydrogen gas here. So the alkali metals are strong reducing agents. The reducing nature of these alkali metals will be decided by releasing capacity of electron from their lost shells and releasing capacity of hydrogen from the acids or from the water or from the alcohol or from any compound containing acidic hydrogen. So the reactivity towards water increases down the group. Lithium reacts with water gently. Sodium melts on the surface of water, whereas the other metals easily catches the fire with water. So from that variation we can identify that the reactivity of alkali metals towards the water is increases down the group. This is about the reactivity of alkali metals towards water, and we will discuss about the properties of these hydroxides after the completion of total chemical properties. So this is reactivity towards oxygen and reactivity towards water. Next property, reactivity towards halogens. Alkali metals, when reactive with halogens, they form MX type of ionic crystalline colorless halides. As you have 2x towards the left side, 2mx will be formed, 2m is the required. So when alkali metals react with halogens, they form mx type of ionic crystalline halides in which the m is in +1 state, x is in -1 state. We have one small variation, that is reactivity towards a particular metal reactivity towards a particular halogen. We see here reactivity towards a particular metal means when a particular metal react with different halogens, how the reactivity varies in a group from top to bottom. Reactivity towards a particular halogen means when a particular halogen react with different alkali metals, how the reactivity varies in a group from top to bottom. First case, let me take reactivity towards a particular metal, means here the metal I am taking the sodium, and the halogens like fluorine, chlorine, bromine and iodine. When these halogens react with this particular metal, how the reactivity can vary in a group from top to bottom of these halogens. Means definitely we know fluorine is highly reactive non-metal, so that on moving from top to bottom, reactivity will be decreases. Reactivity will be decreases. So the order of reactivity of halogens is fluorine greater than, chlorine greater than, bromine greater than and iodine. This is the order for reactivity of alkali, that halogens. Next, reactivity towards a particular halogen, means a particular halogen react with alkali metals. See here, alkali metals are lithium, sodium, potassium, rubidium, cesium. For example, here we will take a particular halogen fluorine. When this fluorine react with this alkali metals, what is the variation of reactivity in these alkali metals? We need to discuss now. In the last session, we have discussed the reactivity order of alkali metals. Alkali metals are highly reactive in nature, and the reactivity will be increases from top to bottom. Therefore, the reactivity increases. So the order of reactivity for alkali metals is lithium lesser than, sodium lesser than, potassium lesser than, rubidium than cesium. So cesium is highly reactive towards a particular halogen. So what is happening when they contact with halogens? Means when they react with the halogen, they are making MX type of ionic halides, which are crystalline in nature and they are colorless. So in which the M is in +1 form, X is in -1 form. Reactivity towards a particular metal of halogens, the reactivity order of halogens will be decreases down the group. Definitely fluorine is highly reactive metal, highly reactive non-metal towards the particular metal, and reactivity towards a particular halogen. So the reactivity order of alkali metals will be increases from lithium to cesium. That is reactivity towards halogens. Next, reactivity towards hydrogen. When alkali metals react with hydrogen, they form MH type of ionic hydrides. Hydrides are the binary compounds of hydrogen with other metals in the periodic table. So these are MH type of hydrides. M is the alkali metal. The nature of these hydrides is ionic in nature, in which the hydrogen is in -1 form, M is in +1 form. So 2MOH, 2M is the required. Alkali metal when react with hydrogen, they are making MH type of hydrides. The hydrides are in ionic nature, in which the H is in -1 form and M is in +1 form. Reactivity towards hydrogen decreases down the group of these alkali metals. So reactivity towards hydrogen decreases down the group. As these are ionic hydrides, these are with high melting point. These hydrides, on moving from top to bottom, the stability of the hydrides decreases and the reducing nature of hydrates will be increases. Stability of hydrates decreases, reducing nature of hydrates increases. So, what is the relation between this stability and reducing nature? See, reducing nature or reducing character of these hydrates is inversely proportional to stability, because when the given hydrate is less stable, they can easily produce the hydrogen. Capacity of producing hydrogen is called reducing character. The compound is participating in oxidation, so that stability of the hydrates on moving from top to bottom decreases and the reducing character of hydrates is increases. What is happening when they react with the other reactants means they are surely making some stable compounds, as these alkali metals are highly reactive in nature. When they react with oxygen, they are making several oxides, means 3 forms of oxides will be formed by alkali metals, and they react with water, they are reacting with water with vigorously they are reacting, and that reaction is the exothermic process. Next, towards halogen they are making MX type of hydrates, towards the hydrogen they are making MH type of hydrates. Next, complex formation. Alkali metals have some abilities to form complex compounds. Formation of complex compounds is the characteristic property of transition metals. However, these alkali metals also forms that complex compounds. In complex compounds we have coordination sphere. In this coordination sphere we have the central metal atom or ion including ligand. So, ligand is the space which can donate the electron pair to the empty orbitals of central metal atom or ion, which can make coordinate covalent bond. Coordinate covalent bond. Central metal atom or ion is acting like electron pair acceptor. Electron pair acceptor is called Lewis acid according to Lewis acid base theory. Ligand is acting like electron pair donor. This electron pair donor is called Lewis base. So, electron pair is transferring from ligand to central metal atom or ion. The capacity to form this complex compound will be decided by some factors. One is smaller the size, higher the charge, availability of vacant d orbitals. When the d orbitals are available and vacant, these 3 are the factors will be useful to form the complex compounds or the coordination compounds. In these respective alkali metals, what is the variation of formation of complex compounds? Formation of complex compounds means we know the variation of ionic size from top to bottom. So, what is that variation? From lithium plus to cesium plus, the ionic size will be increases. Due to increase in the ionic size, capacity to form complex compounds will be decreases, because one of the factor which decides the formation of complex compounds is smaller the metal ionic size or the metal ion size. So, if the size of the ion is less, the ease of transferring of electron pair from ligand to metal ion maybe takes place. That is why the easy of formation of complex compounds takes place. So, what is the variation of this property means? On moving from top to bottom, capacity to form complex compounds will be decreases. So, next solubility in liquid ammonia. Alkali metals are highly soluble in 100% ammonia because the alkali metals are ionized into its ionic form. Solubility in liquid ammonia. When alkali metals dissolved in liquid ammonia, actually these are highly soluble in liquid ammonia. What will happen when they dissolve in liquid ammonia means, when alkali metals dissolves in liquid ammonia, the alkali metal ionized into its ammoniated metal ion and ammoniated electron. So, what is the equation which expressing the solubility of alkali metals in liquid ammonia is, M is the alkali metal consider, X plus Y moles of NH3 is taking we have in the equation. So, the ammoniated metal ion will be M NH3 taken X, as the alkali metal is with one outermost electron in the last shell, they involves in the loss of that electron, that is why M will be changed to M plus 1. So, this ion is ammoniated metal ion. We have ammoniated metal ion and ammoniated electron will be formed with Y moles of ammonia. This is ammoniated electron with Y moles of ammonia with negative charge. Due to liberation of this free electron in the solution, that solution shows blue in color. After dissolving alkali metal in liquid ammonia, the resultant solution express blue in color Y. Means whenever we have free electron, that free electron absorbs some energy and it may excited into some higher energy levels, and while they coming back to ground state, definitely it emits the radiation in the form of color. That is what the liquid ammonia solutions of alkali metals express blue color. This is about the solubility in liquid ammonia. Alkali metals are highly soluble in liquid ammonia due to the ionization of alkali metal into its alkali metal ion and ammoniated electron. Like this, we have some chemical properties for alkali metals. The compounds formed after the reactivity may be with some characteristic properties. So, what are the characteristics of the compounds formed by alkali metals is the topic now. Characteristics of the compounds formed by alkali metals. So, first type of compounds, oxides. Just now we have discussed about the oxides. When alkali metals react with oxygen, they form these three types of oxides: M2O type of monoxides, M2O2 type of peroxides, MO2 type of superoxides. These oxides are basic in nature. One of the important property of these oxides is basic in nature, because When they dissolve in water, they produces MOH type of hydroxides which are strong basic in nature. Or when we take these peroxides when dissolves in water, they forms MOH type of hydroxides, also liberation of hydrogen peroxide, means 2 MOH we required, 2 H2O we required. Whenever we take this superoxides when they react with water, they forms MOH type of hydroxides with hydrogen peroxide along with the liberation of oxygen. Means here we need 2 H2O, 2 MOH, 2 MO2. This is the balanced equation. When peroxides and superoxides are react with water, they are making hydrogen peroxide, they are liberating hydrogen peroxide and oxygen along with the common product MOH type of hydroxide. As they are liberating this excess of reducing agents like hydrogen peroxide, and here one of the product is oxygen, due to this property this M2O2 and MO2 are strong oxidizing agents. Oxidizing agent participate in reduction. Loss of oxygen is called reduction. So these two are called strong oxidizing agents. And another important property of these oxides is, especially we take this superoxides, the superoxide ion formula is O2 minus 1. This O2 minus 1 is with 3 electron bond. What is the structure of this superoxide ion? Means O bond O having 3 electrons and 2 lone pairs of electrons are present on each oxygen, which is with minus 1. This minus 1 leads to get 1 unpaired electron in peroxide ion. Due to presence of this peroxide ion, the peroxides are express some color property, whereas these monoxides and these peroxides do not have any color property, whereas the superoxides shows color property. This is the structure of superoxide ion. The superoxide ion formula is O2 minus 1, it is with 3 electron bond, and due to this minus 1 we have 1 unpaired electron in the oxygen molecule. Therefore, the superoxide ion express the color property, whereas these peroxides and monoxides do not have any color property, they forms that colorless MOH type of hydroxides when they react with water. These are the some important properties of oxides. Next, important properties of halides. Properties of halides. See, M when react with HX, MX type of M when react with the halogens, they can form MX type of halides, as we have 2MX, 2M is the required. Or metal oxides when react with mineral acids like HX, here we will get MX type of halides with liberation of water. Or M2CO3 type of carbonates of the respective alkali metal react with mineral acids like HX, here we will get MX type of halides, also water and carbon dioxide. So this is the preparation techniques or preparation methods of these halides. One of the important properties of halides, one is melting point, boiling point, and solubility, covalent character, ionic character. Very important, this is identifying covalent and ionic character for the respective halides, their melting points and their solubility will be decided by three important concepts, three important terms, three important properties. One is polarization effect, number 2 lattice enthalpy, number 3 hydration enthalpy. These three factors decides the melting point, boiling point, solubility and covalent ionic character of the respective halides. So let me take the first factor, polarization effect. What is polarization effect? How it affects the properties of halides is the question. Polarization effect. So what is the term actually? Polarization or polarization effect means the metal ion of a respective halide M plus, here I am taking, when M plus approaches the halide ion X minus, the M plus cation affects the electron cloud of X minus. The positive charged nucleus of this cation disrupts the electron cloud of this X minus towards itself. This process is called polarization effect. So what is polarization effect? When the metal ion of one halide Mx approaches the halide ion, the electron cloud of this halide ion disturbed with the effect of this M plus. The process of distortion of electron cloud of halide ion by the metal ion is called polarization effect, and that power is called polarizing power of or polarizing ability of metal ion. The tendency of distortion of electron cloud of anion by metal ion is called polarizability. This is polarizability, and the capacity of metal ion to distort the electron cloud of anion is called polarizing power or polarizing ability. This process is called polarization effect. This polarization effect mainly depends on number 1 size of anion and cation, charge of anion, charge of cation, and the fourth factor is electronic configuration. As I told you just now, this polarization effect affects the melting point, boiling point, solubility, covalent character and ionic character of the MX type of halides. How it affects these properties is the question now. Before we are going to that concept directly, let me explain to you about the polarization effect briefly. What is the polarization effect means? When the metal ion of one MX type of halide approaches the halide ion X minus, it distorts the electron cloud of this anion towards the metal ion. That power is called polarizing power. The capacity of the tendency of electron cloud to distort by the metal ion of this halide ion is called polarizability. This polarizability, this polarizing power will be decided by these factors: size of anion and size of cation. For this purpose, let me take two different sized cations and two different sized anions. So for example, here I am taking one small sized cation, one large sized cation, two different sized cations I have taken. And to explain about the anion, here also I am taking one small sized anion, one large sized anion here I am taking. Smaller the size of cation can disturb the electron cloud of anion very easily, because of due to small size the nucleus force is more on the electron cloud of the anion. So smaller the cationic size favors more polarizing power than the larger sized cation. Next, two different sized anions. Whenever we have smaller sized anion, the electron cloud of this smaller sized anion is strongly attracted by the nucleus of this halide ion, and this electron cloud will not be attracted by the metal ion strongly towards the nucleus of metal ion, so that the polarizability is less whenever the anion with small size. When the anion with larger size, the electrons present in the outermost shell of this X minus easily attracted by the metal ion which is with small size. Therefore, larger the size of anion, polarizability is more; smaller the size of cation, polarizing power is more. This is about the first factor. Next, charge of anion. When charge of anion increases, size of anion also increases. So charge of anion is directly proportional to polarizability, is nothing but directly proportional to polarization effect. Charge of cation. When charge of cation increases, size of the cation will be decreases, because number of electrons will be decreases. Effective nucleus charge on the outermost electrons increases, therefore size will be decreases. So charge of cation is directly proportional to polarizing power. This polarizing power is directly proportional to polarization effect. Next, electronic configuration. Whenever the two different cations with almost same or same size with different configurations, here we will take. For this property, here I am taking Cu plus 1 which is with 0.96 angstroms, Na plus 1 which is with 0.95 angstroms. So very less difference, 0.01 difference. We should not consider the difference. Almost those two cations are with same size, but the electronic configuration is different. The electronic configuration of Cu plus is what? 2, 8 and 18. This Na plus 1 is what? 2 and 8. This configuration is called pseudo inert gas configuration. This configuration is called inert gas configuration. When you take this Cu plus 1 in pseudo inert gas configuration, due to presence of this d subshells, due to weak shielding effect of this d orbitals, the nucleus of Cu plus 1 distorts the electron cloud of anion easily when we compare with the polarizing power of Na plus 1. Polarizing power of Na plus 1 is less because in its inert gas configuration, S and p orbitals are there, they are with strong shielding effect. Therefore, nucleus force totally will be on the strong screens, not on the electron cloud of anion. That is why this Na plus 1 is with less polarizing power compared to Cu plus 1. So, Cu plus 1 is with more polarizing power. This polarizing power is directly proportional to covalent character. How it follows that relationship we will discuss now. Polarizing power is directly proportional to covalent character. See, this is the cation with M plus 1. This is symmetrical electron cloud of X minus. When this M is with more polarizing power, the electron cloud of this X minus will be distorted like this. Will be distorted like this, means the electron cloud somewhat moving towards the M plus 1 as it is attracting that electron cloud towards itself. Due to this distortion, covalent character of the compound will be increases, ionic character of the compound will be decreases. Here the lesser polarizing power, more ionic character, more polarizing power, less ionic character, more covalent character. For example, we will take one application. Here I am taking sodium fluoride, sodium iodide. For the same respective metal ion, here I have taken different halide ions. So, Na, FO, Na minus, in these two compounds, which one shows more covalent character, which one shows more ionic character is the question now. See, the ionic character or covalent character here will not be decided by the size of Na plus 1, being it is common in the given two compounds. So, that character will be decided by definitely halide ions F minus or I minus. Size of F minus is less, size of I minus is more. So, whenever the larger size of anion is there, polarizability is more, means distortion of electron cloud by the cation will be easy in case of NaI. So, polarizing power is more for this Na plus 1 ion, therefore, NaI is the more covalent compound, NaF is the more ionic compound, because distortion of electron cloud in NaF is less. So, like that we will discuss about the covalent character and ionic character. Next, lattice enthalpy. What is lattice enthalpy? Means the amount of energy required to break down into its gaseous constituent ions of 1 mole of ionic compound is called lattice enthalpy. Let me define once again. When 1 mole, the amount of energy is required to break down 1 mole of ionic compound into its gaseous constituent ions is called lattice enthalpy, or we can say the amount of energy is released when 1 mole of ionic compound is formed from its gaseous constituent ions is called lattice enthalpy. Let me take once. M plus X minus gives Mx plus energy, or Mx plus energy gives M plus X minus, which are in gaseous phase. So, in any way this energy is called lattice enthalpy. Higher the lattice enthalpy, melting point and boiling point will be more. So, melting point, boiling point will be decided by lattice enthalpy. This lattice enthalpy will be decided by the sizes of the cations and anions. If higher the lattice enthalpy is more, means the melting point and boiling point of the respective halide will be more. Next, hydration enthalpy. What is hydration enthalpy? Means when 1 gram mole of gaseous ion dissolved in water, the hydrated ion of the respective gaseous ion is formed along with the liberation of energy. That energy is called hydration enthalpy. Higher the hydration enthalpy, solubility of the respective halide is more. So solubility and hydration enthalpy are directly proportional with each other. So polarization effect deciding this character, lattice enthalpy deciding this character, hydration enthalpy deciding this character. So the properties of these halides will be decided by these three factors. One is the polarization effect, lattice enthalpy or lattice energy, and hydration enthalpy or hydration energy. So these are the characteristic properties of the compounds formed by alkali metals. What we have completed still now about the oxides, properties of oxides we have completed, and the properties of halides also completed. So remaining portion I will be in continuation with you in the next part. Thank you.